Our presentation today is titled A Multi-Scale Analysis of Retention and Transformation of Phytochemical Compounds in 3D Printed Infant Food under Different Post-Processing Regimes. In simple terms, this study explores how different post-processing methods affect the preservation and transformation of natural bioactive compounds in 3D printed infant food. Our goal was to understand how we can retain maximum nutritional and functional value in printed foods designed specifically for infants using natural ingredients and gentle processing methods. The 3D food printing market is expected to reach around $7.57 billion by 2034, showing how rapidly this technology is expanding. However, most existing studies and applications focus mainly on confectionery and adult diets, with almost no research on phytochemical retention in 3D printed infant food. Incorporating natural bioactives like chamomile extracts into 3D printed infant food can offer both functional and soothing benefits, but there is a major challenge, as these bioactives can be heat sensitive. During thermal or freezing processes under fabrication and post-processing, phytochemicals can degrade or transform, affecting both the nutritional quality and bioactivity. This gap motivated us to explore how processing methods influence phytochemical preservation in 3D printed infant food. For this study, we designed formulations optimized for extrusion-based 3D printing, ensuring proper viscosity, balance, and infant-safe texture. Our base ingredients included sweet potato, which provides a natural carbohydrate and nutrient-rich base, HPMC, or hydroxypropyl methylcellulose, which serves as a structural binder to improve printability, chamomile extract, chosen as a source of flavonoids, particularly apigenin, offering antioxidant and soothing properties, and finally green apple pectin, which acts as a natural gelling and fiber component. Together, these ingredients form a printable, nutrient-dense matrix suitable for infant consumption. We then characterized the samples using different techniques, which I and my group members will talk about. The first one is UV-VIS spectroscopy to evaluate color and optical properties after different post-processing methods. On the left, you can see the comparison between freeze-dried and air-fried samples at different temperatures and time. Time of treatment, especially air frying, reduced reflectance due to Maillard browning and surface darkening. In contrast, freeze-drying retained the original color and higher reflectance, indicating minimal pigment degradation. On the right, we examined how varying HPMC concentrations affect optical properties. The enhanced signal near 330 to 370 nanometers suggests better preservation of chamomile flavonoids in the polymeric matrix after freeze-drying. Overall, these results highlight how freeze-drying more effectively preserves color in bioactive compounds, while air frying may compromise them through thermal degradation.
Here we use optical microscopy to view the surface microtexture. The top row shows untreated samples and the bottom row shows freeze-dried samples. The columns increase HPMC from 0%, 0.5%, 1.5% to 2%. We can see that freeze-drying consistently produces lighter, more porous surfaces than untreated samples. As HPMC rises, the network becomes more connected, with 1.5% HPMC giving the most uniform, continuous texture. At 2%, the surface turns irregular and overcompact, suggesting phase separation. Next, we compare the air-fried surfaces under two thermal conditions. The top row shows 120 degrees for 15 minutes, and the bottom row shows 180 degrees for 5 minutes. We can see that with gentle heating in 120 degrees, the surface remains lighter, while 180 degrees yields darker, smoother, and denser textures. As HPMC rises, the network generally becomes more connected. Around 1.5% HPMC, we observe the most uniform, continuous morphology, while at 2%, irregular density domains appear, suggesting overcompaction or phase separation.
This slide presents a comparative structure analysis using ISDN across varying HPMC levels. As depicted in Fig A, the absence of HPMC leads to a loosely organized microstructure with large irregular voids. With increased addition of HPMC, specifically 0.5% in Fig B, there is clear network enhancement through considerable pore space remain. Notably, the 1.5% HPMC sample in Fig C achieves the most favorable architecture, characterized by a uniform network and well-distributed smaller pores, indicating optimal structural integrity. In contrast, the 2% HPMC sample in Fig D demonstrates signs of overcompaction and irregular void formation, which can be attributed to possible phase separation. Until now, our research team has explored formulations and printing conditions to meet food safety standards. Looking ahead, we plan multi-scale characterization to advance this work further. Mechanical profiling with a texture analyzer will provide crucial insight into printable texture and mouthfeel. FTIR spectroscopy will be employed to illustrate molecular interactions, while HPLC will enable precise quantification of phytochemical compounds. These integrated techniques will strengthen our understanding of how processing parameters and composition interact to shape both nutrition and structure in 3D printed food. Thank you very much for your attention. Looking forward to any questions or discussion.